Thank you. It is a pleasure to be here. We're going to talk about the beautiful Weil conjectures and A1 homotopy theory, and then we'll talk about some new math, which is joined with Margaret Balloon, Wei Ko, Padma Srinivasan, and Isabel Boyd, and some ongoing work with Tom Bachman. And it's Padma's birthday today, so happy birthday. So let's start with the Weil conjectures. So we're going to so F is E mod P, the integers mod P, and F to the M denotes the unique finite field with the elements. And there's a celebrated paper from around 1950 where they studied the solutions to A naught, the equation, A naught x naught to the C naught plus A1 x1 to the C1 plus AN xn Cn equals B, where the C's are positive integers, the A's are integers, and the B's are integers. And
he was at University of Chicago, 1949. Just saying.
He wasn't at Lehigh? No? Well,
I thought he was at Chicago.
Congratulations. I mean, it's a beautiful story. Well, maybe that's not a beautiful story. It's a fascinating, effective. Let's look at the solutions mod P to this equation that he was studying, perhaps at U of Chicago, but certainly in the United States. And so these are the solutions mod P. The solutions in F P to the M. X naught, X1, Xn, and F P to the M, satisfying this equation to such that star. And this paper found a lovely connection between these number of solutions over these finite fields and the topology of the points over that are valued in C. Let's let BI C be this Betti number, the dimension of the singular cohomology XC field coefficients. So Betti number, or the number of holes of dimension I in this shape X of C. So, for example, the 0th Betti number of S2. So for B1 C, the B0 is 1, the B1 is 0, and the B2 is 1. This two-sphere. And the Weil conjectures say the following about how the number of solutions to these equations over F P to the M are closely related to these Betti numbers. So the Weil conjectures which is a theorem work wrote in the lead. Is that so projected? We're about to make it projective. Oh, thanks. Says that if X is the scheme associated to a set of polynomial equations, whose complex points looks like a manifold in the sense that its Jacobian isn't going to vanish, so it's smooth and it's compact. It's like saying projective over a cube. Then we can put all these numbers of solutions over fp to the n into a generating function. So that n equal the number of solutions. And we form a generating function. And m t to the n minus 1 as n goes from 0 to infinity. And this is the logarithmic derivative log of a rational function. That's the same as the derivative over the rational function. And this rational function has to do with these Betti numbers. So it's a quotient of polynomials with 0 to 2 of t all the way up to twice the dimension p. So we've got some polynomials pi with even indexes in the bottom and with odd indexes at the top. Where each of these is a polynomial with exactly pi of c roots. So it's j, so I will be the index of our polynomial. Our roots are going to be indexed by j. They're going to be this many of them. 1 minus, here's our root, alpha ij t, or it's our inverse root, where alpha ij is an algebraic integer, so the solution of a monic polynomial of absolute value q to the I over 2. And the fact that this absolute value, or so the root is q to the minus I over 2 absolute value, is the analog of the Riemann hypothesis. And moreover, there's a functional equation. So these are going to come from things about the cohomology, and the cohomology of a manifold is self-dual. So this functional equation says that if we call this product zeta, such that if you take zeta 1 over q to the dt, then up to a sign, we get the zeta function back again, shifted by the Euler characteristic q to the d Euler characteristic of x over 2 t to the x t. So this is not only a lovely connection between points over a finite field and solutions over C, it also has a lot of applications. Sample application is due to Ellenberg, Venkatesh, Westerlund. And they let X be a space called a Hurwitz space of covers of P1. Hurwitz space of covers of P1, and they computed some things about X of C, and they related this to asymptotics. Of the number of points over various finite fields. And then because a space of covers They use this to talk about sizes of torsion in class groups. So part of the some Cohen lens grid heuristics. On class groups of function fields. Was shown in this very successful relationship. So the aim of the present talk is to replace xc by x of r to the extent to a more limited extent. So the aim is to relate x of r with these solutions over a finite field. And the method is, if we keep track of more kinds of cohomology theories and more homotopy theory, and we work in A1 homotopy theory, then we can do this. And then for our enjoyment, let me say that people also care about x of r as well. So just some fun things about x of r. Reasons why there are conferences on real points of varieties. Or, so if you let x be certain moduli spaces of principally polarized varieties, with some flag data, like think of a modular curve with a level n structure, polarized abelian varieties plus flag data. Then P naught x of r is related to sizes of groups of orders in OK, where K is a number field. So it's a finite, it's a field which is a finite extension Q.
I ask real points? You think of that as just the complex points, and then you have this involution that's complex conjugation. And so it's a ConCMod 2 group action.
Yeah, that's
And can you just try to run through this stuff, but like Z2 equivariantly or something? Or?
Yeah, you can also try to do that. There's so Peter has a beautiful article on Smith theory. There are definitely other ways. That, I have personally tried to do that with some Breton cohomology, but that's not the way we'll do it today. Okay. But yeah, I share that impulse. So in non sort of general all math area versions of this talk, there are other kinds of cohomology theories at play, and that is one nice thing that using A1 homotopy theory can give to this story. But yeah, I don't know. Another advertisement for X of R, which will work great in an equivariant setting too, is I like this fact that Maxwell conjectured, and it's still open, that if you put 3-point charges in R3, at most 4 equilibrium points, but Morse theory is still open because the bounds for Morse theory aren't that good, but people still think it's that. And this is also a real points. This can be expressed as real points of variety. So there's some fun things about real points of varieties I thought I'd share. And as we were saying, the approach we're going to use to say something about this, is to use A1 homotopy. So let's say some things that are also just fun and powerful about A1 homotopy theory. This is due to Morel and Blavatsky in the late 90s. And we'll make this fun. So let's let polynomial equations determine schemes. These schemes, like the parabola corresponds to spec c xy over y minus x squared, and then let's let a1 be the line over R. It just looks like a straight line, and this could be spec c over x or spec r over x or spec k over x for a field, and then so usually in schemes, because they're algebraic, we can't glue or crush. So in topological spaces, we can glue, crush, or really AKA take colimits. Or homotopy colimits. We usually can't do this in schemes, but we then allow ourselves, we then build this A1 homotopy theory where we can, so usually can't. So e.g. So in A1 homotopy theory, we allow ourselves to take colimits of schemes. And let's start with smooth schemes. Smooth schemes are the analogs. Smooth schemes are analogs of smooth manifolds. And we allow ourselves to take colimits of schemes, or homotopy colimits of schemes. Schemes. And this gives us spaces like Pn over Pn minus 1. So when we build projective space, we can build it inductively by adding a cell to Pn minus 1. And then this gives us something like a sphere. And its C points are of dimension 2n, and its R points are of dimension n. And then we allow ourselves to do this, and then we declare that A1 is equivalent to the point. Yeah, so let's write that down too. Then we declare that the map from A1 to the point, some base, maybe spec K, is equivalent. You can do this in much more generally than just with the field, but let's take K a field of characteristic not two. Oh, you do one more thing, which is there's this Nabich topology that covers in a certain topology correspond to colimits. When you glue together the things at the cover, you get the space back. So let's let smooth K be smooth K schemes. And then what you could do is take a homotopy theory of Krishi's topological spaces, or let's say special sets, and then inside this you force take his David sheaves, which are A1 invariant, and you localize the whole homotopy theory. There's some sort of motivic localization, and then this is spaces in A1 homotopy theory. So there's a homotopy theory of spaces, and it's got in here, it's got both smooth schemes and simplicial sets, and you can crush, and you can take colimits. With license to do such things, let's talk about the degree of a map between spheres. Roughly, it counts the images, the pre-images of a single point. So if we have a map of from a sphere to itself, and this square brackets means A1 homotopy classes, Morel shows this is isomorphic by a degree map to not the integers, but a ring called the Grothendieck bit group of K, and let's give some notation for it. GW of K is the Grothendieck bit group, which would be
when you said something about C points and R points of a sphere, so there are some functors, realization functors to topological spaces.
correct.
Topological.
Yep. Yeah. The unstable homotopy category got functors C points and R points. And then we can combine the degree of the real points and the complex points, like as follows. And so the Morel shows that the target of the degree, so the Grothendieck bit group, so this is just the Grothendieck bit group of K. This is defined to be the group's completion. So adding formal inverses of isomorphism classes of non-degenerate symmetric linear forms from some vector space. It's got to be finite dimensional to K, and these can all be diagonalized over a field. So this has generators that are forms on the vector space, which is simply K. We'll call these generators angle bracket A, and this is a bilinear form on K that goes from K to K, K cross K to K, and it's bilinear. It takes XY to AXY. It turns out there are just a couple relations for a field. So the relations, but it makes a ring by saying A, B, the tensor product of these two is AB, and you can do a re-diagonalization of the diagonal matrix AB, get A plus B plus AB, A plus B.
A1 homotopy category you can do over any restriction of the characteristic just because we're going to yield points.
It's just to be a little cowardly about maybe this is stabilizing. It's because quadratic forms and characteristic two, they're no longer. This is all true in characteristics. It's utterly unnecessary. I apologize. So there are a couple of ways the real points.
What does bracket? It's bracket of Pn.
It means the colimit where Pn minus one goes into Pn, and then you crush, and then you map Pn minus one into a point, and you take that colimit. And you're just allowed, you've allowed yourself to, but. And our realizations interact with this probability fit group through invariants of quadratic forms, like the rank and the signature. So the rank from GW of K to the integers takes this bilinear form, sends it to the dimension B, and then we have a signature for K inside R. We can base change to R. And then over R, I forgot a relation. So if we change the basis by multiplying by B, then what we get is AB squared. This is the same as A. So over R, after multiplying by a square, all the A's are either ones or minus ones. So anything over here is going to look like some number of ones, some number of minus ones. And the signature of this beta is I minus J. There's a whole list of invariants of quadratic forms from the Milnor conjecture. And the first one of those, besides the rank, takes the determinant of the grand matrix form of your bilinear form. So this goes to K star over K star squared. And it takes theta to the determinant of theta, some basis Ei Ej. So for example, we're going to be interested in varieties over finite fields, and then the growth of the fit group of FQ. It's isomorphic to just the first two invariants from a Milnor conjecture, which says that you only need as many as the tall dimension of the field. So as a group, this is isomorphic to Z cross FQ star over FQ star squared via taking the rank and the discriminant. As a rank, let's pick a non-square class so that we get something non-trivial. So Q and FQ star over FQ star squared. And then as a rank, we adjoin Q. And if we take U squared, we get 1. Take 2, U minus 1. We also get 0. So that's GW of FQ. And we can pick up both real and complex degrees by the following. We have a map, let's take K and R, a field inside R. So particularities characteristic on 2, as you say. We can have Pn homotopy classes of maps from Pn over Pn minus 1 to itself. And we can take C points, and we get homotopy classes of maps from S to N to itself. We can take R points, and we can get homotopy classes of maps from Sn to itself. And now we have this topological degree, and it hit Z. It counted with a sign, the pre-images of a point, and we have another topological degree, and it hit Z. And this hits the growth of the fit group of K by Rell's computation of the degree. And if we want to get the degree on the C points, we take the rank. And if we want to get the degree on the R points, we take the signature. So an example degree that'll come up later, and we'll get some notation for, is that if you take the nth power map from P1 to P1. So that's the polynomial function. Z goes to Z to the n. That's a degree n polynomial function. So it's better to have rank n. It's over the real points, its degree is either 1 or 0. So the degree, the A1 degree of the map from P1 to P1 given by Z goes to Z to the n, it's this 1 plus minus 1 plus 1 plus minus 1. The sum is I goes from 0 to n minus 1 minus 1 to the I. And this, let's just call this n sub epsilon. So it's like n because its rank is n, and that's just the definition. Definition of that. Okay, let's go back to our aim, which is to connect x bar with x at UVM, and now this is with the loop Srinivasan, Boyd, some in progress work with Bachman. So if X is any object of a category with appropriate structure, a symmetric monoidal category, X dualizable means there's some sort of dual. And if you have an endomorphism of X, then there's a trace of that endomorphism. And the example to keep in mind is on finite dimensional vector spaces. So V, finite dimensional vector space, is indeed dualizable. And then if you have F from V to D, that can be written as a matrix Mij with choosing some basis. The trace of F is then the sum of Mii, but this can be viewed as a map trace from Hom in vector spaces V to V to Hom in vector spaces from K to K that takes F is the composition from K to V tensor V dual, which takes 1 to a sum of EI tensor and dual basis corresponding to the identity map, and then you take F tensor 1 V to V dual, and then you can evaluate if you have a vector and a functional, evaluate the functional along the vector. And that's another way to view the trace. So if you have an appropriate structure, if you have a tensor product, etc., you get a trace in endomorphisms of a certain unit, like K. So for X smooth and proper, X smooth and proper over K implies X is dualizable in stable A1 homotopy theory. In stable A1 homotopy theory. The trace of an endomorphism, let's put F, an endomorphism of X. The trace of F is Morel's degree applied to a map from a sphere spectrum. So this sphere spectrum, if you define stable homotopy theory, spectra will come up, and it has all of those spheres we saw before. So this has T1 over T0, T2 over T1, Tn over Tn minus 1, and we're going to have a map from these spheres to themselves, and it's going to be a map, the degree of a map from X to the dual of X, F so the identity x, the dual of x, to the sphere spectrum, and so it lands in the growth of the big group. So let's define the zeta function, the logarithmic derivative of the zeta function, to be this formal power series, picking up the trace of powers of endomorphisms. Definition: x smooth proper over k, and f x to x, then the a1 zeta, the logarithmic a1 zeta function of x, let's define that to be the sum of the trace of the m power of f times t to the m minus 1 in the growth to be big group with k power series adjoint t. So, for example, if in the case where we were looking at it in the Weil conjectures, that that rational function was a zeta function, and if x moved proper over that q, then the rank applied to d log zeta 1 of x is d by dt log zeta of x, the classical one that we had in the statement of the Weil conjectures. In fact, this is also a motivic measure. You don't need smooth and proper. You can define it just on any class in the growth of the group of arrays. The Kapranov has a motivic zeta function that lands in the growth of the group of array. That's actually not the same as applying. If you apply point counts to that one, don't get this. Apply compactly supported Euler characters, we don't get those. They're just they are different. Compute what they are. They're not the same. This can be computed on a computer by a Lefschetz fixed point. So Huayhua's version of the Lefschetz fixed point theorem says that if you take the trace of f, this is a sum over the fixed points, x, it's fixed by x of some index at f. The fixed points of Frobenius f the Frobenius then the fixed points is the same thing as the set of FQ points, and it follows that this logarithmic zeta function x is determined by the number of points over the finite field as follows. So it's the formula when you work out what the fixed point formula says, d log zeta a1 x of t is the sum over m of the sum over d dividing m of the number of points whose residue field is q to the d. That's the same information as these numbers. I'll write that down. Times very explicit element of the growth of the bit group that I'll also write down. So transfer from FQD down to FQ of 1 times t to the m minus 1. So here, here, alpha d is equal to the number of points of x viewed as a scheme with points with k of x equal to f q to the d. In other words, they're determined by Mobius inversion from these same numbers. The numbers of these numbers that we started with, the number of solutions over finite fields, that's just the same data. So this is the sum over d dividing m. This is just Mobius inversion of alpha d, etc. So this is the same. That's the same data, and this trace is just an explicit quadratic form. This is equal to d if d is odd, and it's d minus 1 plus bracket of a non-square class if d is equal. So that means that you can compute these all day long. And for example, if you have y squared equals x cubed plus x plus 1 over the finite field with 13 elements, then a non-square element is 11, and d log zeta a1 t is 18 plus 179 plus bracket q times t plus 2,106 t squared plus, and I won't write anymore. As another example that we can compute with this calculation right here. So let's now, with a little bit of generosity, compute d log zeta a1 for Pn. Here's the definition of an epsilon. It's this degree of z goes to z to the n. So example, p to the n has cells. It has a 0 cell, a 1 cell, all the way up to an n cell. The Frobenius z goes to z to the q acts on it. And in the beginning, we said that the zeta function was this pi's. They had the number of roots as the Betti numbers, and if truth be told, it's the action on the cohomology, on a tall cohomology. So when if you believe that there's a cellular cohomology, f on h1 kind of cell, this would just be z goes to z to the q from p1 to p1, because that's the one cell. And on the I cell, f on hi cell, this is the smash product I times. The n cell is the smash product of I copies of z goes to z to the q. So the degree, this has degree q epsilon. And on the I cell, this has degree q epsilon to the I, and indeed, the logarithmic data function for Pn is what happens if you take a logarithmic derivative of the products. That is p log zeta a1 of Pn is equal to d log product over I even 0 to n of 1 minus q epsilon to the it plus minus 1 times d log 1 over product I equals 1 to n, but I odd 1 minus q epsilon to the it. So here's the action on the ith cell. And some of these have to be in odd degree when you take the real numbers, you get a -1. So there are cohomology theories that work very beautifully for cellular cohomology, and that compute these d log zeta a1 for cellular systems. So let's describe connection with the topology of the real points. So this is not for modular curves, precisely because we need a cohomology theory that works really well for modular curves in this context, and you get to finiteness questions and motivic homotopy theory, which are notoriously difficult. So what you want to do is have better cohomology theories around. But nonetheless, there's the following connection. And it says that if we had a scheme over the real numbers, x and over R, then the sign, the signature applied to d log a1 xf of t is equal to ddt log of a product of pi minus 1 to the I, where pi is the determinant of 1 minus, is the characteristic polynomial of f acting on the singular cohomology of the real points. With coefficients in some field. And part 2 says that in the presence of the list of Frobenius, so suppose x over d 1 over d with f, then d log zeta, if we reduce over to some finite field, x over f cubed 1 f, this is a power series, and even if we don't, this is a power series in minus 1 and m for m dividing d. It's image in the growth and decay group. So these are generators. There might be some relations for them, but you can express it in terms of just those numbers. And if you take the signature, a star holds. So you can apply this to any toric variety. So remark, a hypothesis 2 holds for toric varieties. And you can do fun things with this. So
Larger.
okay. You can get cancellation. Notice there's no claim about weights. There was a Riemann hypothesis, and you can get cancellation happening here, but you can get lower bounds on the real Betti numbers of R. So let's let this
numbers of the real points.
dimensional view. For example, you can have a criterion to have an R point. in this toric case, or in this case, when you have a lift of Frobenius, which is very restrictive. So when Q is conquered in 3 mod 4, and you're we would say over spec V and F, then X of R being the empty set implies a combinatorial condition on these solutions. So it implies that they'll all end if you take the discriminant of the product, sorry, of the sum of d dividing m of this. These are the number of solutions over fq to the d. Then this explicit phrase fq to the d fq of 1. Then this discriminant is trivial if and only if x f q to the m is congruent to 0 mod 4, and there's one more condition that it's also implied. And for example, this shows that just by counting the number of points over finite fields, because you can also count the number of points that P2 has over a finite field, it implies that P2 has a real point, which is definitely obvious. However, we got this from just knowing that P2 was defined over Z, and you could, define its Frobenius just by writing to the Q over Z, and then counting its points over finite fields, and then all of a sudden know that there has to be a real point. Similarly, we can take a quadric. So let's take in P3, let's take a quadratic equation. So let's take 5x0 squared plus x1 squared plus x2 squared plus x3 squared equals 0 inside P3 over f7. So this is x. X is a restriction of scalars of f7 squared over f7. This is also f7 squared, since f7 does not have a square root of -1. This is f7 adjoining a square root of -1 of P1. And then if you look at what the cellular, what happens on the cells, you get the
P1 cross P1, or
yeah, that's a great point. When this is over the algebraic closure,
oh, I see.
this is P1 cross P1. The Frobenius acts on the 1 cells by flipping them, and then so that makes the logarithmic derivative of the zeta function no longer this thing with only 1s and -1s. The u comes in there critically. The log zeta a1 for this x, its 0 cell and its 2 cell look just as normal. So this is 1 over, here's the 0 cell, and here's the 2 cell. Epsilon squared t. But on the 1 cells, what you get is minus u d by dt log 1 over 1 minus q epsilon again times u. This is true for any restriction of scalars to the quadratic extension. So this u is changing depending on what your finite field is. Plus minus 1 d by dt log 1 over 1 plus q epsilon t. So you could also take the restriction of scalars from z adjoint 1/2 with I and run part 2. And so we can take u equals -1 and take the signature of d log zeta a1 x t. And here we just get d log 1 over 1 minus t squared. But here, this becomes a plus 1, but this was a minus 1, and these become the same, so they cancel out. And using part 2, we get that v0 of r plus v2 of r is greater than or equal to 2. Let's see that. So if we take so we could also take the restriction of scalars from C to R of P1 and compare with P1. This has C points over C. These two are the same. So this is the quadric in P3 under some appropriate restrictions, and the C points are the same. They're a P1 cross P1, but the R points. So when you restrict scalars, actually, it's defining properties. So if you didn't know what restriction of scalars was, now you can wake back up. So the restriction of scalars from C to R, if you take the R points, that's the same thing as the C points and without the restriction of scalars. So that's a S2, and this is an S1 cross S1. And so this actually implies that the classical zeta functions for the identity, classical of the identity equations, classical zeta.
Here you said the second Betti number, oh, sorry, the sum is going to equal, sorry. So in this case, it's equal to 2.
So the classical zeta functions are the same. And as you're pointing out, the real points, the Betti numbers, was the example we had when b naught equals 1, b1 equals 0, b2 equals 1. It was our example Betti number from the beginning of the talk. So this one is what's getting seen there as well. And these classical zeta functions are the same. But because of the behavior with the real points, and part 1 says that the A1 zeta function is going to be that, but the A1 zeta functions are different. Okay. What we like to do is to, instead of spreading out the entire Frobenius, instead what's important is to spread out a cohomology theory. And so there's some candidate cohomology theories, and we give in the paper we give a result for Morel and Savant's cellular cohomology, and Tom Bachman and I have work in progress related to some conjectures of Morel on extending that theory to cellular schemes, but let's stop there.
Any questions? I just had a question about the statement of the theorem. So in part 2, what was the hypothesis on
The whole Frobenius list.
Frobenius? Yeah. What was Frobenius list of the example then?
It's from the restriction of scalars with z adjoining 1/2 and join I to the there's a list of Frobenius that swaps the two factors on that raises to the cube on each factor.
Sorry, so it's something in equations.
Yeah. But I mean, it's really more like the restriction of scalars. I wouldn't write it down on the quadric.
Oh, okay, that's right.
Sorry, yeah.
So I think you mentioned you have some kind of style of homology. Roughly say how to define that.
Yeah, so there's there's an A1 derived category, and there's a derived category of the heart. Mapping into the A1 derived category, and the C cell is a left adjoint or a partial left adjoint for this inclusion. So the if what's in the Morel you take C1 of X, which is a way to take a motivic homology of X, which is quite infinite. And then what they do is they find C cell of X with the properties that C cell X to any complex here is what you would get in the A1 derived category. Here. So the analog, maybe the better thing to say is this. So let's do this. Let's think about cellular homology in topological spaces. So you have abelian groups or Z modules, and you can map them to spectra via the Eilenberg-MacLane spectrum, and then take the derived category. There's a C cell, which is left adjoint to taking the Eilenberg-MacLane spectrum on the whole derived category. And so you know that this respects tensor products because you construct it. You construct the cell in the singular, they're weakly equivalent. And the singular homology, that's a nice tensor functor, and well, it's left adjoint to what would happen if you took the Eilenberg-MacLane spectrum and geometrically realized, and so you want to do the same thing with A1.
Any more questions? Finding like the H of K for the like embedded into the probe issues. So they were A1 variant stated issues. Can you spell anything out about like what the stated topology is, and also like what is it by A1 variant?
Yeah, so A1 invariant means that the X plus A1 and the X equivalent. So in the David sheet, means that if you have an David cover, this is an étale cover. So étale means you're an isomorphism on tangent spaces. So the étale, it also means that your fibers are separable field extensions. So it's unramified, it's flat, unramified. That a nice way geometrically to think about that is it's just a map that locally on tangent spaces is also an isomorphism. So it's an étale cover, taking care of the algebraic separability issues, etc. Such that for every point, there exists some I and ui and ui, such that ui is mapping to x, and the associated field extension, sorry for the lousy forward, k of x into k of ui is a nice and so then being a native sheet means that f of x is a limit of the f of y's to the f of the ui's over x. As in the sheet condition, if you're two different restrictions, here are some double overlaps. Your two restrictions to the double overlaps. So